Welcome to the workshop. Today we want to take a look at power series representations of functions. And when we look at the examples for this, we're actually going to be considering a relatively particular collection of examples. So we're not looking at just any old function at all. We're looking at a few examples where we can make a connection to the geometric series. So this first example is incredibly basic, so that way we can really see the connection to the geometric series. So first, let's recall what a geometric series might look like. So a geometric series looks like the sum from n equals 0 to infinity of a times r to the n. But what's so nice about the geometric series is that we actually know what the sum of the geometric series is. And it is exactly a divided by 1 minus r. This is incredibly convenient for us. Certainly, we know that it converges when the absolute value of r is less than 1, so we have a convergence. But it allows us to consider functions that have a representation that looks similar to this, or that can be manipulated to look similar to this. We have a lot of capabilities here because we know that we can add and subtract series, so we know we can look at functions which can be written as the addition or subtraction of such things. We also know how to represent the integral or derivative of series, right? We know how to represent series which are integrals or derivatives of another series, or take the integral or derivative of series. However you want to phrase that is fine. Depending on our viewpoint for the example, you may phrase it either way. So let's see here. So we want to compare this form to that form. And if we were to simply say, well, let's consider let a be equal to 1, because that's what's in the numerator, and r be equal to x, then we would have 1 over, well, actually, let's write it as the geometric series first. The sum, if a is 1, then it's just 1 times x to the n is equal to 1 divided by 1 minus x. But that is exactly f of x. Okay. The sum of a times r to the n is equal to a divided by 1 minus r, which is our function f of x. So this actually gives us a power series representation for f of x, which is centered at 0, because it's x minus 0 to the nth power. So again, the power series representation is exactly the sum from n equals 0 to infinity of x to the n. But it would be nice to determine the interval of convergence for this as well. And while the examples that we have discussed use the ratio test to determine first the radius of convergence and then the interval of convergence, we actually know that a geometric series converges for r, the absolute value of r, less than 1. So we don't have to use the ratio test in this case. We know that geometric series converge for the absolute value of r less than 1. In r, in this case, it is just x. So the series, the power series that is, converges for the absolute value of x less than 1. That tells us that the radius of convergence is 1, and that the interval of convergence is from -1 to 1. Now, you might be saying, well, Dr. Reynhout, don't you need to test the endpoints? Well, yeah, when you're using the ratio test, you do need to test the endpoints because the ratio test is inconclusive when the absolute value is equal to 1. But in this case, we're talking about a geometric series, and we know that a geometric series diverges when the value for r, the absolute value for r, is equal to 1. So we know that it diverges in this case at -1 and +1. All right, and that's all that we're looking for there. The power series representation for the function centered at 0, and we wanted to find the interval of convergence. It's not asked for here, but of course such things are of interest to us. Thank you for your time. I look forward to seeing you guys again in the workshop for another example in power series representations of functions.